Okay, let's move on to the second keynote lecture this morning. So our second speaker this morning is Dr. Yi Wang from FM Global. Let me first introduce Dr. Wang. So Dr. Yi Wang is the Staff Vice President of FM Global and the manager of the Fire Dynamics Group in the research division. At FM Global, he oversees the research activities of CFD fire modeling, material flammability, fire dynamics and testing, as well as battery fire safety. Dr. Wang serves on the editorial boards of Fire Safety Journal, Fire Technology, and Fire Materials. He chairs the Fire Research Colloquium of the International Symposium on Combustion, upcoming this summer in 2024. He is also a committee member, scientific program co-chair of the International Association of Fire Safety Science. Let's welcome Dr. Wang to give us a speech.
Thank you very much, Professor Chen. It's a great honor to be able to speak here as a keynote speaker in the 19th Open Forum workshop. I remember the first time I attended this conference was about 15 years ago. That was the first symposium workshop in Montreal, Canada. That time I worked on Open Forum about 1 year, present early work of FireFOAM, and it's really very, very pleased and happy I'm able to present the work for the last 15 years from myself and the group, my colleagues, and it's a very big honor for me. A little bit about myself. A lot of times I wear 3 different hats. The first hat I wear is a CFD developer, like a lot of you guys. I was trained at a fluid mechanics major, and later on I was educated as a combustion scientist. So a lot of work is not CFD modeling, but physical modeling. Understand the combustion physics, heat transfer physics related to fire. But the third hat I'm wearing is more a user, an engineer, and also a product manager on a tool which can help us to understand some phenomena, solving engineering problem. So I think throughout this talk, I'm going to wear more of my third hat. So you're gonna listen from an industrial perspective, how and why we develop a FireFOAM, and how what's our goal, and how we use it, and what's our wish list, okay? Hopefully it's useful for you guys. Okay. All right, first, what is FM Global? Who is FM Global? FM Global is established around 200 years ago, 1835. We are the largest insurance company. Only problem is nobody knows about it. Because we don't really insure any, individual properties. No cars, no residential house, health, insurance, life, we don't deal with that. We only specialize in the commercial and industrial properties, okay? If you happen to work with one of the large corporate, like Huawei or Intel or Boeing, the likelihood of your company being insured by FM Global is about 30%, okay? That's why we are the largest insurance company in this industry sector, okay? And the company believe our majority of the loss is preventable. This loss prevention is achieved by research and engineering. That's why, our work relevant. We can see how our CFD work come into play, right? So the kind of the hazard and risk the company is dealing with is fire, and explosion, and also equipment hazard. There's a picture that's missing. I don't know why. But also all kind of different natural hazards: earthquake, hurricane, wind, flood. But fire and explosion actually account for roughly 50% of our loss as an insurance company. So it's very important for us. That's why we need to understand our risk. So this is a typical problem that our engineers are facing. When they walk into a client facility, looking at this, this kind of a warehouse or distribution center or manufacturing space, we basically see a lot of combustible material, which could be anything. Okay, plastic, battery, cardboard, wood, fabric. They also can be stored in certain height, under certain ceiling, and with all kind of different configuration, the flue space, the aisle, all those things matters in terms of how fire develop, how big the risk fire will be. And also we need to figure out the suppression. Basically, our engineer will ask, hey, how bad the fire will be if there's ignition? Okay, that's a risk evaluation. If the sprinkler, the fire protection, will work if there's a fire. Okay, if not, what do we need to do? Okay, should we change our design? Should we change the protection? That's a risk mitigation. Or should we change the storage configuration? And also, if there's the risk is too big, what should we tell our underwriter? Should we buy reinsurance, or should we just walk away from this risk? So those are risk selections. Okay, everything is based on engineering knowledge, so we can do our risk evaluation and mitigation, and also inform our underwriting decisions. Okay, we have a tool to help us. The tool is typically the full-scale fire testing. So basically, we know what material being stored. We reproduce it in our lab, which is the largest lab in the world. And we just look at the sprinkler design, if it's adequate. For this specific case, it's a 40 feet of storage, 8 tiers, under about 45 feet of ceiling. The material is plastic. Okay, and we are putting a sprinkler in every 2 tiers. We call in-rack sprinkler, so there's a pipe inside the rack storage. So we want to look at how the protection works or not. Okay, as you can see, there's something. The experiments are very expensive. It's more than $100,000, taking several weeks, and it's very hard to instrument. Imagine you putting a thermocouple in the fire, it's going to be burned. And the laser diagnostic wouldn't work. If you have a good camera or IR camera, you might see through it for some time. When water comes down, visibility, even for IR camera, you don't see a lot. We're basically getting a global solution to the protection work or not working. Then there's tons of parameters in the real world, in the design. Everything will change, the behavior, the nonlinear behavior coupling of the physics. We don't really understand a lot, all right? So to change that, we want to predict a model. That's why a lot of industry are doing CFD. That's one of our reasons. This is our goal. We want to build a predictive capability for industrial fire and suppression, like this, okay? But when we started back in 2008, that's a capability within the open foam. Hiram Weller sent me a code, say we just developed a buoyant foam, which is pretty good for buoyant flow. That's a good starting point. It actually is. And at that time, in open foam, there's a premix flame solver, which is based on Hiram Weller's PhD research. However, fire is really a non-premix flame, so we need to building a combustion model from pretty much scratch based on the fluid mechanics turbulent buoyant flow solver. So where we are now. So we actually, for selected material, which are important to us, we can do fire growth and fully coupled fire suppression for pretty much any arbitrary geometry height configuration. We can look at the ceiling sprinkler activation pattern, ceiling temperature, heat release rate, different angle. We use this to design the protection, but also to communicating to our engineer, educate to our engineer, and also educate our client. So there's a lot of pre-compiled simulation scenarios, so our engineer could show this to client to say, hey, this is why your protection is not adequate. There's a what-if statement, scenario. Basically, if you change a certain parameter, and certain protection, you could change your hazard level, reduce your hazard. So gain, some credibility. Think about it, if one engineer who have never do large-scale testing want to convince the CFO to invest in $10 million for fire protection engineering project, with this kind of tool, it's much powerful. Okay. All right. Now going to some technical part. What is FireFOAM? Different people have a different definition of FireFOAM. Certainly, FireFOAM is a solver within OpenFOAM, but it really is a package. And to us, FireFOAM, we really coupled all the things in the gas phase and in the liquid phase, solid phase, discrete phase in the spray, and also handle thermal radiation, which is wavelengths and direction dependent. For all these different phases are achieved in a multi-region model. Basically, solid field have its region and mesh, liquid film have its region and mesh, and gas phase has its mesh. So this multi-region mesh is coupled, through the boundary condition and mass transfer and energy transfer. So I like to call FireFOAM a 4M model. It's a multi-region, we just talked about it. It's capable to handle multi-phase flow, again, solid, liquid, gas, discrete, and couple all this physics and dealing with multi-scale, both in terms of land scale and time scale. We need to model a warehouse about 30 meters high for about half hour to 1 hour. This is a huge simulation. And sometimes the time scale of the flame and heat transfer and the water droplet is really small. All right. So before we handling the big coupled problem, we need to looking at sub-physics to tackle the model development, co-development, and also the separate effect validation. So here we start again from thermal proof. We look at turbulence model. We look at entrainment. We look at the subgrid scale modeling. And also for fire plume, we look at the flame height, entrainment, and when they're hitting the ceiling, a ceiling jet. Near wall, we want to look at the heat transfer convective wall function and soot and radiation in the fire. So all this heat transfer and fluid mechanics are key component of fire growth before we can couple it together. In the suppression part, we also started from working on fundamentals. With a sprinkler, we need to understand atomization, which is input condition, the droplet size, velocity, flux distribution as the input condition, either from experimental measurement for any sprinkler type, pressure, or from a CFD, the kind of VOF simulation to provide the input condition we need for FireFOAM. The next state is spray plume interaction. Basically, you have a droplet, a Lagrangian particle tracking, how the spray will penetrating through strong fire plume and to really land to the top of the solid surface and wetted surface. And when there's a water form a film, how the water film flow, those physics need to be developed. And also, there's a gas phase flame extinction when there's not enough oxygen, not enough high temperature and water cooling, and how to model extinction. All right. I'm not going to go to all this. Sorry, I'm not going to go to all these details of validation, but we have to understand we need a lot of experimental data and separate effect cases, canonical problem to validating each part of the model, submodel. I want to highlight two very important submodels within FireFOAM. One related to fire growth, the other related to fire suppression. The difference in between combustion problem with fire is combustion is open loop problem. You provide amount of fuel, you're looking at how this fuel burns, the power, the heat generation, the temperature, and also the pollution. But fire, we really never control the amount of fuel coming into play. It's all dependent by itself. So the gaseous flame will generating heat, and heat transfer back to solid fuel will determine how much flame spread and really burning. The pyrolysis of the solid fuel really feeding to the gas phase to burn. So that's one of the key of fire modeling. All right. Second is suppression based on water. I'm going to touch it later. Pyrolysis model. For example, we want to model corrugated cardboard. Okay. And you can see this is structure of corrugated cardboard. Really a porous media, non-homogeneous, different layers. Even thickness of each layer and density of each layer are totally different. So it's a lot of physics for each different fields. The things we really want to do to try to simplify it, The way we simplify it, we first assume there's a one-dimensional heat transfer, okay? And then we assume the material is homogeneous. Then we assume that's one-step Arrhenius reaction. So with this simple assumption, the problem is trackable. If we really want to model every single detail, the problem is never going to help engineering solutions, okay? When this simple basic model are breaking, are not working, we need to think about what new physics we need to add to be able to model the physics. But let's start from a simple physics. That's basically the foundation of our pyrolysis model. With this equation set, really the problem how to getting all these parameters. There's about 10 parameters. Heat conduction, CP, the Arrhenius form, parameters. What we do is putting material in the under some bench scale apparatus to burn it, at a different heat flux. We measure very important parameters, output, for example, the mass loss rate as a function of time, at different heat flux level. Also, we measure surface temperature, back surface temperature, all these important parameters we want to capture. What we do is we plug this into our model and do the reverse engineering to getting the property. If this, optimized property could provide this exactly same behavior to a satisfying level, we think we are all set, okay? We plug in our pyrolysis model and property into the gas phase solver, the FireFOAM solver. The first validation is the parallel panel flame spread, vertical flame spread. We compare the model, which is solid line, with experiment. We have two repeats. Don't look at this gray line because it's a sensitivity study, okay, for different work functions. But what we can achieve is, okay, the area under this curve is total energy that generated. It's pretty good. Okay, the maximum fire size is predicted. The time to start and the slope are good enough, and also the decay behavior are well captured. Right? Okay, this is actually the simplest possible situation that we can model. The material is relatively simple, the configuration is simple, and there's not much feature you need to capture. The next step, we are happy with this validation. Next step is moving to a more complex scenario, which is rack storage configuration. Here we compare two configurations. One is 3-tier, the other is 5-tier, shown in this picture. On the left-hand side, those are experiment image. On the right-hand side, those are modeling results at different time. You can see here is more difficult. Here, of course, we need to capture the difference of a maximum fire size, for different two configurations. The model will capture very well. But the whole curve is not a very easy fire growth curve. You can see there's a lot of different phases. Each phase have a different slope and have a different change of slope at different locations, which actually corresponding to different physics. At this stage, we're looking at a vertical flame spread on a vertical flue space. On the second stage, you can see fire starting to spread to underneath box to have certain horizontal flame spread. So you can see the pickup of the fire spread rate. And then here, the fire growth rate is much higher, is because the flame is actually projected from underneath of box to all this, four vertical surfaces. Suddenly, the surface being involved in fire are increasing dramatically, so is the heat release rate. And later on, you have another horizontal spread phase from the center two column to the side columns. Okay, the model actually captured very well, okay, for both height. So this gives us a lot of confidence. So we have certain predictive capability for this kind of field. We can predict a scenario which we never have done experiment, which is non-tier configuration for free burn. In our lab, we can never do free burn because we need to put in water to cool it down pretty soon. Otherwise, the whole building is going to be burned. All right? But as you can see here, you have vertical flame spread, lateral flame spread, another vertical flame spread on vertical surfaces, and you can predict what's going on, the hazard. We can show this as a what-if scenario to our client. If you don't have adequate sprinkler or you don't even have a sprinkler system, you're in big trouble. My mouse is not working here. Okay, let's forget about it. I think you can imagine pretty soon the fire growth will going to accelerating, and it's going to burn the whole field pretty soon within several, maybe a couple of minutes also. All right. The second component of important component in FireFOAM is this liquid fume model. We need this liquid fume model to couple the whole suppression and even couple between the solid phase, gas phase, as well as the droplet discretized phase. This is also a free surface flow, but we don't want to use MVOF to track all of them. It's computational, very expensive. We don't need to do that. Simple assumption is we just assume the liquid film is very thin. We neglect all the gradient within the film. We only integrate the equation on the vertical direction. So we're getting the equation for thickness, which is mass conservation, and the equation for velocity, and also for temperature. Again, this schematic is showing the coupling between the film model with droplet model. You have impingement, splashing, separation, dripping, and also you have all kind of mass and energy transfer between the liquid and the hot burning surface. All right. We also do separate effect validation. This is a very interesting experiment. Here is experiment image. This is a simulation. We are changing two parameters. One is the increasing the flow rate from the top to bottom. Here we have a more water flow rate. You can see there's a more wet space when increasing the flow rate. And also we actually having a heat fast heater to heating the water film. And you can see when we have a higher heat flux, there's a more dry space, especially in the low water flow rate conditions. So, when we couple the film flow with a parallel model and also with all other physics, we can achieve the fully coupled suppression case. Again, compare our model result with experiments for quite a lot of different configuration, different flame, different storage height, material, and also the water flux. You can see here you have a pre-wetting region, and also you have interaction with water with burning material. Okay. All right, now we have fully coupled simulation for selected material. I showed example of class 2, which is corrugated cardboard, but also we have a model for more complex field we are using to design sprinklers. Here it's a plastic cups. Inside the box we call CUP or class 3 CUP commodity. And also we have plastic pallet, which uncartoned material we call uncartoned, unexpanded plastic. We also have a model for roll paper, model for organic liquid. I'm going to show some of them. And we're working on a Paris model, fuel model for batteries too. Okay. How we do more complex fuel? For example, for this configuration, we call CUP commodity. Outside is the same car box, so it's this thin layer in the schematic. Okay, we have a lot of cups within this three-dimensional space, and we keep the same model for the liner board. But when the liner board burns through, we need to understand how this cups burns. What we are doing again is we're getting one of this unit, putting into our bench scale, burning apparatus to figure out its burning rate. Instead of dealing with all the detailed heat transfer between the cups, three-dimensional heat transfer radiation, and also all this divider of cardboard, we actually treat it as one unit we call outer unit. It's attached with one-dimensional pyrolysis region. Whenever this car box outside being consumed, we just trigger the burning of this kind of unit. Of course, when this outer unit burns through, we are burning really in depth. We are dealing with a more global model, which we call inner unit cell, really to distribute all the energy into all the different burning area. Okay, when it's burning through. So this kind of combined, first principle modeling with some phenomenological engineering model really hit the balance of, the fidelity we need for engineering problem solving. Okay, this is a validation. Again, compare our model image with experiment for a certain height. We also have this kind of result for different height. You can see the simulation matching with 2 repeat experiments pretty well until the end. What happens is here, in experiment, you have a lot of plastic start to dripping and forming a pool underneath. The model did not have the capability at that time, so we're actually underestimating certain area is burning. Okay, but still, this is it's good enough for us to do our engineering calculations. Another very interesting model development is paper rolls. We ensure a lot of paper manufacture facilities. They really are trying to store this big paper roll they call mother roll. Each roll is about 2 meters high and about 1 meter diameter. It's huge. Then when they get in this roll, it's stored in the storage. Then they kind of cut it to different shape for different purpose and sell it. All right. The paper have a different material. You could have a newspaper, you could have a craft paper, you could have tissue paper. They are burning differently, and also you could store differently. So sometimes they have a gap, sometimes they are butted to each other. All these small things changing dramatically the fire grows. We need to model that. Here you can see this is one of the picture that we put in this paper roll into our burning apparatus. What you can see, the problem is not really a one-dimensional heat transfer anymore. You have this distinct delamination process really driving the heat transfer. As soon as the paper breaking through, you are not losing heat to the back of the surfaces anymore. Your heat transfer suddenly changes, you're burning very fast. So this thermally thick changing to thermally thin behavior is very important to capture. Okay, so that's why we have to enhance our one-dimensional homogeneous Pearson model to adding this physics. But also this delamination and physics is also not a one-dimensional, not local phenomena. You can see whenever you break in a large row. This is a large experiment. We're putting a bullet camera in between. You can see you have a propagation of peeling, and you have to capture those effects. Be able to really capture, predict, and validating the large burning. So we actually do the validation for 2-tier, 3-tier, 4-tier, again similar. This is a comparison between a modeling and experiment. So again, that gives us confidence that we can do prediction. The prediction would be, we know how the raw paper burns when it's stored in 40 feet under 60 feet ceiling, but we don't know how it burns when it's stored in 82 feet under 100 feet. This is our proposal from our client. We want to store this way. This is the largest experiment we can do in our test facility. So of course now you already see water starting to putting down. The fire is reduced already. Otherwise our building will be collapse. Basically you can see this is the time you need water to come down. This is the time that very fast flame spread, but when you get into this range, it's a 30 megawatt per second fire growth rate, very, very large. It's like a big generator. Okay. We can extend, using model to extend application for our limited experiment. This has been a theme for our problem solving. We have using the model to solve all kind of different problems that our client facing. For example, one problem is when ceiling sprinkler is not adequate, how we design in-rack sprinkler at a different interval to be adequate protect. So it's every 2-tier, every 1-tier, or every 4-tier, how to optimize this design. We're using modeling to do that. Also, a lot of industrial property warehouse have a slope ceiling. How the slope ceiling changing the sprinkler activation pattern. You can imagine when you have fire will spread to both ends, but the hot smoke only going to the left region because of slope ceiling. The water will come down here, there's no water come here, then you'll have a disaster. Okay, what kind of slope we can tolerate? How do we design a sprinkler? This is another practical scenario. You have a sprinkler, but a lot of warehouse have we call a smoke vent, skylight. It's really designed for visibility when there's a fire. They want to design for people to have enough time to people to get out, for firefighter to come in. But really question how this smoke vent will changing the interaction of a sprinkler. So we're using model to design that. Of course, we are using combine the model and with experiment. Before, without model, we probably need to do a wider parameter study, maybe 10, 20 experiment. But now with model, we probably only do 2 or 3 experiments. Coupled with model, we can solve the problem. This is another two different problem, example. I don't want to go into all the details. Let's move on. I want to highlight some ongoing research, which is very exciting to me. The first one is the liquid, ignite liquid spill and spread. This is we have a lot of this kind of facility in industrial, manufacturing space. All kind of different liquid aid for painting, for some hydraulic liquid, for insulation. They're all stored in this kind of container called IBC. I think it's about 1 meter by 1 meter cube. That's a lot of liquid. It's been transported by the forklift. What if there's an incident, there's a spill, and there's a hot surface or something, ignition source? What's the scenario? It's important for us to know, but also it's important because when we burning plastic, you can see plastic will drip and forming a pool, and it's almost exactly the same phenomena. You have a spill and a flame spread, but just a different property, different viscosity, different density. You might burn differently with some other liquid. So we don't want to using VOF to do the interface tracking everything to resolve all the same liquid. We recognize we have our model. We can do this kind of spill for water, a pool. Can we using this for ignite liquid? The answer is yes, but no. Yes is we really, really want to take advantage of our 2D film model, but it's not adequate because the assumption of a thin film model, there's only bulk velocity and the bulk temperature is not adequate anymore. If you assume a whole layer of the liquid is same temperature, you never really getting evaporation, never really getting the burn. You underestimate the hazard significantly. So what we need to do, we don't want a 3D mesh. What we want to do is we build an embedded mesh to do the one-dimensional heat conduction. But still, we have this two-dimensional convection, which is also important in heat transfer, which is thermocapillary convection. This is the surface of the field. There's actually this kind of motion-driven circulation, driven by convection, driven by surface tension force because of temperature gradient. Basically, you have a hot, places, you have cold places. There's a flow going this direction, so there's a circulation underneath the surface. So here we are showing experiment and our modeling. In experiment, we can have some like velocity tracker, location tracker. You can see the surface is motion after the heating up. The model actually can predict the similar velocity in the surface. The creative part of this thing is we are not solving the three-dimensional fluid mechanics region. We are building an analytical solution. Actually, it's good enough to capture the circulation. So we have a one-dimensional embedded subgrid-scale heat transfer, but also we have theoretical solution to capture this thermocapillary convection. So the end effect is we can still using a two-dimensional mesh to dealing with this complex spill, free surface flow, and with this complex thermocapillary convection. Okay, this is validation. We're looking at the flame front as a function of time, the location, a function of time for two different kind of fields. Let me try to play the video. I don't know why it's not playing. Okay, this is actually a pretty nice video. Can you help play that video if you can? Thank you. And also, we are looking at the heat release rate, fire side as a function of time. For different liquid. This is low flash point liquid. This is mineral seal oil. It's a medium flash point liquid. It's not doing. Okay, don't worry about it. I have another. The other video is just compare. Okay, this is just demonstration. We are pulling down 50 kilogram of indicating, and I just want to show. The left is basically just showing the spill. Okay, the spill is much faster than flame spread for this liquid. Okay, just because of low viscosity. But then after a long time, the fire starts to develop and starting to spread on this spilled liquid. And the important thing is thermocapillary convection will cool down the burning region, but heat up the preheating region. The burning rate in a fire of origin will reduce, but the burning rate, flame spread will enhance by this underneath convection beneath the surface. Okay, this is also important component when we model this kind of plastic burning, as I mentioned before. So when you have a plastic burning, you have a melting, dripping, you're forming a pool. This pool will spill. We're actually using exactly the same model framework embedded in this model to be able to handle part of the physics. Again, this plastic is high density polyethylene. This is one of the standard commodity for us to design certain sprinkler for certain commodity. Pretty soon you're going to see this experiment that we apply uniform water on top of the commodity. You can see the gas-filled flame getting quenched, but this part of flame is very strong, still going to spread to part of the commodity later, even with this water flow rate. All right, how do we model that? There's two very important physics. One is when plastic melt and burns through, there's a deformation of the geometry, your geometry change. This change of geometry is very important when we're dealing with radiation heat transfer. Imagine you have a matrix here, all the radiation being blocked. You really don't see the flame radiation a lot when you have this kind of configuration. But when you burn through, your heat flux is significantly going through. So you have to model the geometry change. The dynamic mesh come into place for this kind of simulation. The second is the phenomena we just talked about, the pooling and spread. All right. You giving a close examination of this material, you have this we call film region, which is very thick. After burning, this region is still mostly intact. Okay, structurally, we have all this we call lattice region. The material is much thinner. It burns through quicker, so we need to handle this. Okay. Conceptually, we divide all the material in two regions. Film region. In film region, there's no geometry change. There's no dynamic mesh. But in lattice region, we need to deal with differently. In the film region, we pretty much use the same liquid fire model that we just talked about to dealing with the liquid fuel. In the solid side, we basically have one-dimensional heat conduction. And in liquid side, it's we basically have a 2D mesh for each local cell. It's a lumped model. We know the thickness of the liquid. We know the temperature and the velocity. On top of that, we're building on in-depth embedded one-dimensional subcritical heat conduction, and also we have this theoretical solution of thermocapillary convection. Okay, this is a demonstration of how we deal with this lattice region, how we deal with the geometry change. We model the lattice region with a very thin thermal baffle. So we don't mesh the solid thickness. We basically an infinite thin material. And each of the baffle is really attached with a certain thickness of solid. This solid, when heated up, can be changed to part of the material changed to liquid. This liquid is actually modeled by a local parcel. And this local parcel droplet is interacting with melting from solid, impingement from other layers when dripping down, gasification and burning and dripping. So you can see here, you already see the dripping, the pooling. You can see as soon as the solid material reduces to a certain threshold, the baffle will disappear. We're using the attach-detach functionality of a dynamic mesh in open form. They're changing this baffle into an internal first phase. Then the liquid, the flow will go through. All right. We basically couple the solid film region with the lattice region, different region treatment. We can model the fire growth of this commodity compared with experiment. This is experiment, this is our modeling for different height. This is 1 tier, I believe this is 3 tier. All right, just to recap how we do fire growth. We basically have a certain thickness of the film. We call film of the fuel. If this film of the fuel is larger than critical value, it's burning regime. If it's smaller than critical regime, there's no liquid. Basically, there's a solid being preheated. Okay. But when we do the suppression, there's more complexity because there's another layer of film of water and molten plastic. We need to add another film, and also we need another Lagrangian cloud. One cloud is looking at the dripping of the fuel, another is water. Okay, going back to this same carton, on top of solid and the fuel film, we also need to have a water film we call a suppression film. All right, sorry. Basically, when there's a water, the suppression the thickness of suppression film is larger than critical value. Depends on if there's a liquid fuel or not. If there's a liquid fuel, it's a suppressing mode. When there's no liquid fuel, that's a pre-wetting mode. Okay, that's basically, we need to handle this quadrature. Depends on the thickness of the water, thickness of the fuel. We have burning, preheating, and suppressing and pre-wetting, really dealing with all different locations of the interaction between water and fuel. Okay, I don't want to go into the detail, but I want to show a demonstration. It's a similar demonstration for the lattice region. We had a free burn, but pretty soon we're going to apply water with different, rate of water. Here we have a lot of water pulling down. Here we have not enough water. Let's see how qualitatively the behavior of suppression. Now you can see the water. When you have a lot of water, it's suppressed very quickly. Hardly any fuel has been burned. When we don't have enough water, you can see, fire is reduced, but you still have a burning. But you still have the, disappear of the solid burning material. Okay. Again, when we couple the two regions, the frame region and lattice region, we have these two films and two Lagrangian, and this water film interacting with the plastic film only through thermal heat transfer. There's no other, mass transport. It's a simple assumption, but probably good enough. The water film will block the radiation and convection, and does show some correct quantitative behavior. Okay, you can see now this model really pushing this multi-region coupling, multi-physics coupling into extreme. You have all kind of different coupling physics and phases. We are currently in a process of validating a much larger scale validation cases for suppression. Okay, I want to talk a little bit about future direction, the opportunity and the challenging we are facing. All right. Now we only handle limited material we're using to very important for our warehouse fire protection, but we really need to deal with much larger range of fuels in a much quicker pace. Okay, we need to speed up the development of different fuels. For example, facade, PV panel, those fuels are multi-layers, multi-component, totally different behavior. Hopefully we can do it much quicker for different fuels. So for the gas phase, or radiation, liquid phase, I think a lot of physics are universal. So, but when dealing with different fuel, we need to develop a different fuel model in a faster manner. For example, open top container is all robotic enabled facility, and also the water actually have a different behavior because this open top container can collect water. The same fuel model would not work anymore. And also battery. Well, I'm going to talk a little bit more about battery. Battery is everywhere. We insure car manufacturers. We insure battery manufacturers. So there's a lot of storage of the batteries. We also insure energy storage system. Basically the solar panel farm and wind farm, they have energy storage system. So different form factor, different chemistry, we need to be able to model that. We treat it as a different solid fuel. Only different is they have exothermal reactions inside it. Okay. And when it's a fuel, each individual cell being putting together in the module, there's some other component. Sometimes there's a gap in between. Sometimes there's a plastic in between. They're changing the heat transfer and changing also the burning, the heat loss, heat dissipation. So those details are very important. Again, this is a balance. How we balance the first principle of physics with phenomenological modeling, which is practical for large scale. When this fuel is packaged in a metal case, it's a compartment phenomenon. There's not oxygen inside. The fuel is burning outside, but there's certain heat transfer mode inside. All right. This is exciting. Oh, I hope we can show this. It's very nice. Let me try if we can show this video. Yeah, let me try. Oh, too bad. Okay. This is actually a partially populated energy storage cabinet. We only populated 5 of these, modules. All the top is actually inert. We're trying to build a validation cases for the battery energy storage system. I think what I'm going to describe verbally is the ignition. We're going to trigger one of the battery inside, let it propagating, and after about 10 minutes, there's going to be auto ignition, pilot ignition, and there's going to be a flame. The plastic is starting to burn. You have a flame spread, and eventually the thermal runaway of the battery within this container really accelerating, almost like a flashover cases. Each of this module will get into thermal runaway in the same time. Actually, you're going to see a jet flame project to this direction into about 2 meters long. So it's a huge flame. I hope I can show you maybe in a later time. Really challenging is that we want to do it faster. A lot of simulation I showed it taking several days, several weeks. The longest simulation close to a month, using pretty big nodes, typically 200, 300 CPU nodes. It's too long. We really need to speed it up. One thing we want to speed up is using some numerical tricks, the numerical algorithms, AMR, take advantage of all the development of HPC, GPU enabling, and to looking at the data-driven and machine learning surrogate model to speed it up. All right. We actually have some AMR capability in FireFOAM, but it's not good enough. I mean, talking about AMR, Professor Jacek, PhD thesis AMR. So at this point, we still cannot use the full AMR in our industrial simulation. I think we can do better. We need to do dynamic load balancing for all the different phases: solid, liquid, gas, and discrete phase. And also the multi-region refinement, when you have a 2-dimensional mesh, 1-dimensional mesh, how it's being coupled, how can they achieve this dynamic load balancing in the interface of coupling is important to us. Okay, we hope to having some progress on this topic with the help of Professor Jacek. We're also trying to take advantage of the development of the community. There's a lot of nice work has been done by HPC technical committee, by NVIDIA on the linear solver part. This is our the profiling result without using GPU. A lot of effort is using solving the Poisson solver in our cases, and also another high demand is radiation solver. So this is about 50% is using pressure solver. So by taking advantage of AMGX, we actually can reduce this to about a factor of 3 to 4 in the solution time. But overall, it's only 15 to 20% of saving of execution time. If I have to buy GPU to achieve this kind of speed up, I wouldn't do that investment at all. It's not good enough. But the reality is a lot of national labs having a GPU there available. If you cannot enable a GPU, nobody's going to allow you to use that. So there's a little bit of that. But also, this is just beginning. I know there's a lot of ongoing work from Professor Chen's group are trying to speed up all this part, the yellow part setup. And Professor Jacek is just mentioning their work too. I really hope we can take advantage of their development, in next year also to further speed this up. And also we are looking at how to speed up, the radiation part either through GPU or through other mechanism. I'm going to show this. which is a machine learning-based model. Basically, if you're looking at a machine learning-based model, the radiation is really a very good candidate to that. It's really not a transient problem. It's just a mapping between a temperature field and absorption coefficient field, which is your composition of a gas and soot, and to your radiation intensity as a function of space and direction. Okay, there's opportunity there. And we're trying to using the neural network to mapping from one solution, one function to another function. This nonlinear mapping through the operator neural network. We are using one option variation called DeepNet, trying to map between, again, this is two input function. One is temperature, the other absorption coefficient, and the output function is radiative intensity as as a function of S and S. That's the space you need to project to. Okay. There's a nice paper published by Professor Liu from Yale University. They're talking about the structure of this DeepNet. You basically, each of the input condition, the temperature and the absorption coefficient is one branch net, and the projection space is a trunk net. You kind of combine this. There's a theoretical, mathematical proof. There's a certain type of the neural network is available, always available as a solution, mapping solution of these kind of equations. Okay. I'm going to show a test problem for one-dimensional problem. You have a 1D slab at certain temperature. There's a non-uniform temperature distribution within this one-dimensional direction. For example, in our training data set, we could have temperature distribution of this parabolic profile or this kind of profile like a flame, and different profile of water vapor and concentration of your composition space. This is a training data set, then we can looking at the evaluation data set. We compare the radiation source term and radiation heat flux for different scenarios. The machine learning algorithm is actually almost exactly the same as our numerical algorithm, but it's about 10 times faster compared to ray tracing algorithm. But if you're putting this solution into GPU, it's usually 100 times faster. Okay. Currently, all this development is still a separate solver for now. Hasn't been fully coupled with the FireFOAM yet, but that's the next step we're going to do. Another very exciting improvement is when we also shows this algorithm working for 3D problem, but also it's solved inherent numerical changing for Rhe effect. If you only have 8 solid angle, you basically have a big Rhe effect. You can see, your distribution of heat flux is never uniform. It's really the solution, inaccuracy because you don't have enough Rhe. But in the neural network, you can infer any arbitrary directions. You can sum it up. It's really cheap, and you really solve the Rhe effect problem. The ongoing work, we're trying to work on this neural network surrogate model for complex boundary condition, complex geometry, and trying to improve the learning speed, and also trying to basically explore both physics-informed and hybrid data-driven strategy. By example, I did not mention our solution I showed before is physics-informed. Basically, we are using neural network to minimize the residue of the related with heat transfer equation. Okay. The next step is really couple another component with the FireFOAM is data-driven component. All right, just to summarize, we started from here about 15 years ago, and we achieved a lot of growth coupled all this 4M, multi-physics, multi-region, multi-scale, multi-phase. We are able to use the model to solve real-world problems. Some recent innovation related to spill and spread related to the geometry change, again, really pushed this the coupling multi-phase in the extreme in terms of complexity of the model. We're working on the new fuels. Battery is one of them. This is actually one of the picture. It's a big jet flame is projecting out in this direction that I showed. We really want to using any methodology to speed up our simulations. It's extremely important to us. Right? I want to quickly thank our team. This is my colleague Ning sitting here. He actually is author of a lot of nice work and animation I showed here, including the liquid fuel model. And Alex Chrisman, Xiaoyi Lu, and Daniel Mahalis. And also a lot of our alumni in the modeling team has contributed tremendously. This FireFOAM is never it's feasible without experimental support. We have a lot of experimental people to give us experimental insight, small scale, large scale properties and validation data for all kinds of physics, and also our management support. And FireFOAM certainly, we started working with OpenCFD group from the beginning, from day one, initially under the leadership of Henry Weller, later on under leadership of Fred Madoka, Andy, Sergio, has been a key member of working on FireFOAM. Certainly, we benefit a lot of discussion and training from Professor Jacek and Henrik. Thank you for all your input. Appreciate your time.
Okay, we have time for a couple of questions before the tea break. Do we have any questions? Oh, we have quite a few.
Thank you for your very impressive and valuable presentation. I have just one simple question for you. In terms of the company's business, what's the reason for the sharing as an open source of your FireFOAM?
Oh, okay. I mean, I hope I try to make it clear at the beginning. Maybe I was not successful. We are just an insurance company. We insure a lot of this kind of fire problem. For example, think about our premium is about $10 billion. Our loss is roughly $7 billion a year. 50% of loss is fire and explosion, $3.5 billion for fire. So if we can see one fire, it's probably huge amount of gain. That's one part. Another is really development cost and the limitation of experiment. If we want to solve a problem for our client, experiment may have some limitation at some point.
Just to add on that, I think his question was also on why are you open sourcing the code?
Oh, open source, okay.
As a private company, yes.
Oh, of course, we benefited from open source and we need to give back, I guess. There's actually a lot of functionality within OpenFOAM has been funded by FM Global. FM Global has been one of the major founder of this code through different mechanisms.
Okay, I think we had another question from the back.
Okay, thank you for the presentation. I have a question about what can you share about the resources required to run this simulation, like mesh size, cluster usage.
Mesh size and what?
And the cluster usage, how many
codes and
infrastructure
required
to run this?
We have our internal cluster pretty much upgrade every 3 years. We probably invest around $300,000 every 3 years, for buying our internal cluster. And also we have a budget of a similar amount for AWS. So to as overflow, whenever our internal cluster is busy, we're just using cloud. Typical simulation is using 200 to 300 core, for the industrial cases I'm showing. I mean, each simulation could be several $1,000s easily if using cloud. Again, it's taking several weeks, but there's a lot of time to spend on pre-processing, post-processing, validation, everything. That's why, in addition to machine learning-based surrogate model, we also are working on investing some generative language model to pre-processing and post-processing for the code. So hopefully that answers your question.
Yes, thank you. And what about the typical mesh size?
Mesh size. It's several million to 10 million cell. We typically don't go into very big cell mesh size. We're trying to handle the physics in subgrid scale physics. If we have to model everything with a mesh, I don't think we can solve this kind of problem. We have to build in a lot of engineering modeling in there, and also the coupling. But that's a gas phase. But also we do have a mesh in a liquid phase. Usually it's small, but the mesh in a solid phase can be big. But also the droplet is very expensive, and the radiation is very expensive. So gas phase mesh is only one component of it.
Thank you.
Okay, I think it's time to close the first part of the session. If you do have more questions, please approach Professor Wang at the coffee break or later in the conference. Before the tea break, again, we have the small gift for. So Professor Wang have traveled from Boston all the way here. So I saw he was posting photos having barbecue with his daughter, and before he traveled so far. So greatly appreciated.